Hello, I'm Dr. Greipsson, and I will be giving talk about, this title of my talk is right here, the phytoextraction of heavy metals, focusing on lead, contaminated soil using switchgrass, and that's the Panicum regatum. And I work at the Kennesaw State University, that's in Georgia, United States, actually north of the city of Atlanta. Okay, so let me just start here. Okay, so lead is widespread in soil, not only in Atlanta, but in United States and around the world, and come for this different reason, mainly because of this leaded gasoline. So that's sort of made it airborne around highways, old highways, and even into the farmlands. Not in high concentration though, but smelting and mining has, of course, resulted in much higher concentration, but very localized concentration, high concentration of lead. Then lead has been used in pesticide, arsenic, sort of blended with lead. Sounds incredible, but it was used. And then also impurities in chemical fertilizer, and this adds up with time, and sort of gets soil to be at not maybe at dangerous level, but at unacceptably high levels, and especially for our food production. So why are we so worried about lead? Well, lead is not supposed to be in our bodies. And so we should have basically like 0 parts per million if we measure it like in our blood or something like that. But unfortunately, it gets into our bodies. And it has damage, especially damage to young children, especially when they are young and they are like crawling on the floors. And kids that are raised under such condition, they start to show up into like IQ deficiency. This is intellectual quotients. They are not doing well in schools, and that also can be translated into neurological damages, and that kicks in with all type of like social problems. The long-term exposure to this, like we're talking about, like low level of lead, not like a toxic level all of a sudden. This has also been linked to early onset of Alzheimer's disease. Same thing about the Parkinson's disease, but these diseases are, of course, neurological diseases. And then also on other organ systems, sort of a cardiovascular system, immunological, and also into our endocrine system. It has adverse effects. And this has been documented for quite some time. And lead is not needed in our body. It is not needed in our agriculture. And it is usually found in low levels in agricultural soils. We are talking about something like 10 ppm. That is like the background level. And usually these plants have their own mechanism of avoiding taking lead up into their roots and then further translocation. So lead is not in sort of a healthy agricultural or in a healthy ecosystem. So what is the sort of the benefits of like of the soil remediation? Now, a large-scale soil remediation has not really started, but there is certain interest for it, and that can all be sort of calculated into like improved healthcare cost, of course, and then sort of reduces the need of using like primary agricultural land for biofuel production. That is sort of another one, and it increases the land values. There's no doubt about that, and improved land uses. And I think that in the near future, this will be taken more seriously to cultivate our food on soil that is that doesn't have high levels or even medium levels of lead or other heavy metals. Then we're talking about like mercury and cadmium and other such. And so the switchgrass is actually this second generation biofuel crop, and the first generation biofuel crop were, for instance, corn, maize. That was, but there has been reluctance in using the corn because that could drive up food prices, and also to start to use these biofuel crops on primary agricultural land. That could drive up food prices as well. But the ideal situation is to use the second generation biofuel crops, such as switchgrass, the Panicum virgatum, and use it on marginal lands. This is like a land that has not been cultivated before, or has been cultivated and taken out of cultivation. The soil is not very fertile, but the grasses can still grow there. And by using these second generation biofuel crops and cultivating them on marginal land, that could definitely improve our energy security. And that might also help in mitigating some of this carbon sequestration, and might help with the climate with this ongoing global warming. And so let's look at this problems, how they have been in the past. Where does the lead come from? And that has been also a question, because we have lead in concentrated areas where we have like mining and processing, and we have such places even in big cities like in Atlanta. There are several places like that, and now there's an ongoing like a Superfund site going into residential areas. And but lead became very widespread when it got into our gasoline, and this is like an anti-NOx system. And you can see here, this is like we have the year here, 1940, 1950, and then it peaks. But then the problems were sort of like obvious, that this resulted in like neurological problems, especially with kids, like babies that are growing. And then this leaded gasoline was being phased out. And we have here the usage on tons, how it has been spread out. And you can see that it was phased out fairly quickly. There was another chemicals that is being used, and it was just as good, but lead was taken out. Now, lead has also been used in paint, white leaded paint, and that has also been phased out. But old buildings, they could have like lead in their paints, but that is more of a sort of a very localized problem. But lead that gets into the gasoline, this was more widespread, especially into the cities. And the lead is still in the soil. It is in the topsoil layer, just in maybe a thin layer there, but it is sitting there, widespread. And what goes here hand in hand, interesting graph here. Now, this is not from my study, and this is from the study of Mielke. And this shows that there is a perfect match here between the reduction in the lead emission and the blood and the concentration of lead in the blood of humans going down as well. And this has also been sort of calculated, like how many, because when you start to reduce the IQ level of humans, they cannot get education, they cannot get good jobs, and that could all be calculated then in like what is the cost for the society. And there's definitely been a reduction here after the lead was phased out, and reduction in the blood of humans. So this is the children's blood level. Okay, so cities, they have been mapped in the United States. This is the city of New Orleans, quite recent mapping, and things have been improved. There is an ongoing program of but it's just excavating the soils and taking it to somewhere else. I could go on with like maybe 20, 30 similar images of different cities around the world that all show the mapping. And there is usually a high sort of this sort of inside the core of the cities are like this high level of lead. And you see that this has been like phased down. This is from data from New Orleans that shows there from 2005 and 11 to 16. And this is the soil lead it gets up to be like 1,000 here. And in the older data, it gets up to be like 1,500, more than 1,500. But most of the lead is sort of concentrated in less than 500 ppm. And this is the median blood level. And that is shown to be like reduced as the soil, as the concentration of the lead in the soil is being reduced. And the whole the lower 50 states here of the United States, they have been mapped to a quite good degree, and there's like a lead risk here. Now, this doesn't mean that there are like localized, even if this shows like blue color, there are like localized areas with actually quite high lead concentration. And then we have these Superfund sites where industry have been taking place. And so this has all been mapped out quite neatly. And now heavy metals, they show up in certain concentration. They impact the growth of plants. And this is just to show you like impact of lead on rice, actually at sort of not dangerously high concentration. You see here, this is the control plant. And this is like this deep green color. But the heavy metals, they usually mess up or like interfere with the ion chain in the chloroplast, and they cause this like yellowing of the leaves, and the yellowing is then chlorosis, and then that could lead to necrosis. That is basically the death of the leaf that starts here on the tip of the leaf, and so it is going to be reduced growth, and it's also going to impact the physiology of the plant, and like less likely to have seeds. And at a higher concentration, the plants are not only going to show stunted dwarfy growth, they are simply speaking just going to wither and die. So what can be done about this like lead, unacceptable concentration of lead in the soil is that there are several phytoremediation technologies, and they sort of depend on the site and on the cost of the project and so on. And we have here like these different technologies like phytostabilization, phytodegradation, phytovolatilization, and then the one that you'll be focusing on, that is the phytoextraction. And phytoextraction is mainly focused on metals, while the other techniques, they are like focusing on organics and metals also. And and this is when we basically have soil, and we just take the lead out of the soil, put it in the phytomass, or the mass of the plants, and then we dispose of that, and that gets into like industrial uses. And so in the phytoextraction, that is a little bit different than the other technology, is that we need to harvest the plants and get them out. When we harvest them, we are basically taking the metal out there. And that has to be done repetitively, and sites that are under Phytoextraction Act, they have to remain so for at least 5 years. But sort of the limit is not to have it more than 10 years. And but there could be extremely polluted sites when things start to be above like thousands of ppm that could take up to 10 years. And showing it here more sort of these different volatilizations that basically it just gets out of the plant. Phytoextraction, the pollutants, they remain in the plant biomass, in the leaves, in the stems, and it's being harvested. They are also in the roots. Phytodegradation is that sort of harnessing the power of the soil microbes also. Phytostabilization, this is just when we are stabilizing, and that is often done also by putting like chemicals just like phosphorus on the ground. But that doesn't solve the whole problem. And this all deals with the plants. The plants, they have the roots in the soil, of course, and they have like symbiosis with arbuscular microbes and fungi. and they get the nutrients, and along come the metals. Usually the plants, they can sort of deny access for the heavy metals into the plants. They have no benefit for it, but when we freeze up the symbiotic relationship with the arbuscular microsome fungi and use chelates, we get the metals into the leaves. And the plant that I've been concentrating on in my lab is the switchgrass. Switchgrass is a perennial grass that is native to North America. We used a variety named Alamo, and it was derived from Texas. But this is basically a wild plant, and when we seed it, we really have to wait for 2 years to maximize the harvest. And it has a very dense stand, and you see it is harvested here, and it can have dry mass up to about 17 tons per hectare. And the good thing about the switchgrass is that it is not very demanding on the soil itself, and it harnesses the symbiotic relationship with the soil bacteria, the beneficial soil bacteria that are like promoting the growth, and and also with the arbuscular mycorrhizal fungi. And it's easy to grow this grass. There are equipments everywhere around to plow the field, harrow it, seed it, and then start growing it, and then just harvest it, and basically just get rid of the biomass, bale it up, and then it can be used for something else. And in my case, we are mostly interested in this thing that is called the grassoline. And the grassoline is basically when you take the biomass of the grasses and you turn it into ethanol. And I'm not gonna get more into it, but that is like an industrialized process to sort of squeeze the ethanol out of the grasses. And this even made it to the front page here of the Scientific American. And there's a lot of interest in this thing to just turn the ethanol turn the grass into this grassoline or into ethanol. And at the gas stations, when I fill up my car, then I always have the option, or I don't have the option really. It says all the time that at least 10% of the gasoline is ethanol. And there has been certain political debates about this 10% because they would like to have it even more, even higher than 10%. And yes, switchgrass again, this is like the second generation bioenergy crop. It's very useful for that. And for this study that I'm going to talk about, this is because the switchgrass is the candidate for this like dual production of like biomass production for the industry, for the energy industry, and also for phytoextraction at the same time. And the ethanol production in the United States has been increasing, and there was a sharp increase here after 2005. You can see that it was from 1990 to 2005, it was increasing, but this is when it went into almost an exponential growth there. And most of the ethanol production is in the states where we have heavy agriculture, a lot of fields, and it probably comes from corns in like Iowa, Nebraska, and these are like states up north, and the rest of the United States is here. And this data goes from 2016 here, but this has remained. It is growing, but it's growing sort of slowly, linearly. But there's like millions of barrels, more. So it is getting close to 400 million barrels altogether now, the production. And ethanol is exported from the United States and is also mixed in with the fuel and used as such. And I said that the gasoline that I put on my car it is at least 10% ethanol. But there are also also vehicles that take ethanol, what you call E85. That's the other way around. So 85% is like the ethanol. But it's hard to find gas stations here, especially in the south. This is Georgia. This is you see that this is like how many stations there are, and so this is very concentrated up north here around the Great Lakes. So you can drive around here, but you are running into trouble when you get to Montana, and then again you have to get to California and in Texas. They have a good number of these stations, but Texas is large, and then there is like this southern state. They don't have too many. You see, there's only 1 to 9 ethanol stations. That is not going to work well if you want like to travel through these states. So this is one of the sort of the threshold, and also there is a huge competition with the electrical vehicles. But the electrical vehicles, they account only for like less than 10% of the total sale of new cars. Altogether, the electrical vehicles are only a tiny portion of all the vehicles in the United States. And the vehicles, they last for 20 years. So it's going to take, the ethanol is going to be needed for at least next 2 or 3 decades, maybe more. So, and if this sort of energy switch is going to take place, going from like going into the electrical cars. Okay, getting away from that, but that is the byproduct of this high biomass second generation plants, and that's what drives the interest, is that the biomass can be used. This place has been put out there in a use, and we get ethanol out of it, and the lead is being extracted. Lead is heavy, it precipitates, and that's like an industrial process that I am not going to get into, but it is possible today to extract all the metals out of the basically get it out there before it gets into the ethanol. Now, for the phytoextraction, we have basically 2 options. We have an option of using plants that can accumulate heavy metals, but and that happens sort of steadily. You see, we have the growth period, and this is the concentration of that happens. But the problem here is that these hyperaccumulators, they are small plants, and they are not plants that are readily cultivated. They could be like ferns, and I've never seen a field of ferns, for instance, or they're like tiny plants. But unfortunately, they kept them with the same plant. They should have shown something like a corn or a switchgrass here. So the plants that are used on agricultural fields. And then we just grow them, we get a high biomass, we maximize the biomass, and then we do this chemical manipulation. We add in the chelates, like the ETTA, the ethylene diethylene aminoacetic acid, or the NTA. That is another chemical that I'm going to be focusing on, and that is the nitrilo triacetic acid. And these are chelates. They act like soap. They solubilize the metals and get it into the plants. We also add like growth promoting hormones on the plants. And there's a possibility of maximizing the growth and maximizing the inflow. And actually this line here, it should be just a straight line up here. And then the plants are getting toxic effect, and then we harvest them. So this is the metal uptake here, is usually narrow, and then just harvest it. And the function of this method is, or the effectiveness of this method is a function of the biomass and the concentration of the metal inside the biomass. And this is like the experimental setup that I have at Kennesaw State University. We have an experimental greenhouse here. It's a nicely controlled environment, and we have here this the benches, and we fill these pots that are like 5-liter pot with contaminated soil from Cedartown, and it's about 5,500 parts per million ppm of lead. And then we do this manipulation. So this is switchgrass growing here. This is this Alamo variety of the switchgrass, and we grow them and for like 3-4 months and do this chemical manipulation, and then we harvest the plants, and we take it like step by step there. Now the soil that we use has high contamination, lead 5,800 ppm, a lot of iron also. It was a bit worrying factor, 12,000 ppm, and aluminum. and it is a slightly acidic, 5.7. And one of the problem with these two metals is that we could get high inflow of iron and especially aluminum. Aluminum toxicity is actually quite common. And the study that I'm going to talk about now has just been published in the Frontiers in Energy Research, and it's about the phytoextraction of lead contaminated soil by switchgrass, and we were focusing on this BAP and the NTA. NTA is the chelate, the nitrilo triacetic acid, and the BAP is then the benzyloaminopurine, and that increases the growth of this sort of steadily of the plants and makes it sort of more resistant for the heavy metals. And my co-workers there, again, Hart, he was a student of mine, Austin Gilly was also a student, and Marina Kother, chemistry professor, and Thomas McElroy in my department at the Department of Ecology, Evolution and Organismal Ecology at the Kennesaw State University. Now, we were basically testing, like this chelating agent, and because ETTA ETTA was actually used, to get, if people get lead poisoning, then they got to be hospitalized, and they get it in the system, and it takes away the lead. But it also takes away like calcium and iron, so this has to be carefully monitored. We can use it, but in Europe, its use has been banned. In the US, they're sort of, let's try to use something else. That's why we're interested in the NTA. And adding also what they call the alkyl polyglucoside, the APG. This is like a Triton X. This is like a soapy material also. And actually in big restaurants and hotels, they have a different detergent to put when they do the dishwashing. And that includes NTA and APG. And this is like a gigantic like soap, that very, very powerful soap that gets the lead from the soil into the plant. And then we add the plant growth regulator, the BAP, the benzyloaminopurine into it. And this should sort of make sure that the plant is growing well, and then it can tolerate the lead, and then get the lead into the foliage. And for this for this experiment, we have here different treatments, and we have here the control. We did nothing, and then we just add here these are the chelates, NTN plus IPG. The infuse was actually added here to decrease the activity of the arbuscular microbes of fungi, and that is known to sort of increase the uptake. Then we gave them also this 12. This is just the nutrients on like a foliage nutrients, and then we gave them also the bromelain, and then we have here the bromelain is the BAP. Bromelain is done both the infuse and bromelain. This is used in agriculture, so these chemicals are already sort of, they're inexpensive and they could be found in large quantities. And the bromelain has then the BAP, or the benzylaminopurine. So we have this experiment. So this treatment number 4 that has the chelates and the BAP was the most interesting for us, because there we are like checking it out. Is it really needed to add the nutrient or not? And these treatments can be upscaled on big fields. So it's just a question of doing it in a small scale in the greenhouse, and then they could be upscaled on much larger fields to remediate the soil. So we grow the plants, the switchgrass, we just germinate the seeds, transplant them into these 5-liter pots, and we use the soil from Cedartown, that is like 5,800 ppm, and grow them at the research greenhouse in Kennesaw State under controlled condition. We have extra light there, and we water the plants and give them their nutrients, and then we harvest them after 179 days. And this is when the plants started to show some sort of toxic signs, like this chlorosis, and not only yellowing, but also the leaves were turning purple. Then we harvested the plants, and we dry the plants, and we do the acid digestion, And this is a sort of a known method of using the hydrochloric acid and the HNO3. This is the aqua solution. And but we use this in the hot block express system. It's a fairly easy system. And we reflux it at this temperature, almost boiling temperature, for almost an hour. And then we vacuum filter it before we do the analysis. So this is the hot block express system. We just put it in the tube here and put the aqua with it. And then we just maintain it there for 55 minutes. And then we filter the solution. And we did the chemical analysis in the ICP OES. So this is the inductively coupled plasma optical emission spectrometry that we have at Kennesaw State University. And we can actually see the plasma. Try to find the arrow here. Yeah, we can see the plasma here as a light blue. And this one has actually a robotic arm, so we can put many samples, and it just takes one sample after another, and it can measure for about up to 20 elements at the same time. Now, so after plants when they were harvested, we looked into them until the dry mass of the foliage, and definitely the addition of the BAP, the benzyloaminopurine, gave some good effect here in the growth. They were significantly, like, take the dry mass of foliage, significantly heavier than the dry mass of plants in other treatments. And you can see that the control was even lower here than the NTA, and the NTA with the nutrients. Now, NTA can also, like this kid, they can solubilize like nutrients and bring it to the plants. And then if you look into the lead, this was of main interest to us. What was noticeable was that there was a huge variation between the pots, and we got on average here almost 6,000 ppm concentration. Now this is quite high, and one of the pot had actually 10,000, more than 10, just a little bit more than 10. That is like 1% concentration of lead. So this method of adding the NTA here is very effective, and then in other treatment they have here like 4,000, and this is a little bit more than 3,000, and control we are just talking about like less than 200 actually. So without the chelation, there was almost no uptake of lead, phytoextracted lead biomass, and added together. Then of course this method was like outbeating any other one. So it is the best to have the chelate and add the growth, the plant growth regulator, the BAP, into it. Iron, we were worried about iron, but the iron concentration was higher in the plants that were treated with the chelate, which was sort of something expected, but it didn't interfere with anything. But the control had less because the chelate brings more iron there. And the aluminum concentration, this is something interesting, is that it was very high when we had the NTA just on its own. Then it decreased, but there was no significant difference. There was this enormous like variation, and with the control plant it was much lower. But aluminum is problem in the soil that I use here, because when we acidify the soils, then usually we get like a huge amount of aluminum into it. That's why it is a better option to use the chelates rather than acidifying the soil. We have tried that using citric acid, acidify the soil temporarily to maybe pH 3.5, pH 3. We get a lot of lead, but we get influx of aluminum to a dangerous level, just killing the plants. So if we put this in, like, what did we find out here? We of course that the treatment, when we add together the chelate, the nitrile triacetic acid, and the plant growth regulator, the BAP, gave the best results of almost 6,000 ppm of lead uptake. And one of the plants there had actually more than 10,000 ppm. That is like more than 1% of the plant biomass. And excuse me, it has been stated in the past that when plant reach that level, then it is ideal to use this type of methods in phytoextraction. So we could definitely improve this technique of phytoextraction by using the NTA. And NTA is more beneficial than ETTA, because NTA, its half-life in soil is usually less than a week. ETTA lasts longer and therefore has sort of potentially more damaging effect. And NTA is available commercially, and the same thing about the BAP, that is available commercially. So yeah, using switchgrass was very beneficial, about 6,000 milligram of lead plant matter. Now, we have to keep in mind that the switchgrass can produce about more than 17 tons per hectare. This is sort of the optimal production yield that we can expect. And so if we say that we are dealing with a field, we sort of give it this hypothetical sort of situation, extrapolate from this, then the potential phytoextraction, if the soil is 5,500 ppm of lead, that we could get about 103 kilograms of leads per hectare each year. And to get this lead concentration then down to in something like in the hundreds, maybe 100 or 200 ppm, that should take then about 6 to 7 years if we harvest the plants only once a year. With the lead here in the southern part of the United States, usually the plants are harvested twice a year, and that could even bring the yield to a greater level. And of course, soils that are only that are less than 1,000 ppm, they could be phytoextracted in a matter of 1, 2, or 3 years to get to the acceptable levels. That is sort of the potential of this technique. Now, for my sort of future line of research, I have been is to get this into a field experiment. That would be ideal thing to do. And then to get more into the sort of the switchgrass itself, because I told you the switchgrass variety, although it is called Alamo, it has not really been, it's not really a cultivated plants. And some gene editing is going on now. Almost every plant is under some program of gene editing. And we should really focus on the methylmethionine, make the plants more tolerable. And therefore we could maybe increase this, that they could accumulate maybe not only 1%, but get it up to maybe 2 or 3%. That's just hypothetical speculation in increasing the metal tolerance of the switchgrass. And we also notice in many of these fields, there are other pollutants. We have zinc, for instance, and plastics. And there's a lot of interest in what about the plastics in the soil? Are we going to add also microplastics into it? Now, in the end, I have a list of papers that I published recently, and these are my talk was mainly based on these frontiers in energy research. I've been doing studies on the arbuscular microbes of fungi. Also, I have one paper there in the pipeline. We published also in the journal Plants, evaluating chelates, then journal Plant Nutrition, where we are looking into the nutrients addition on the plants. And we also had one study using other foliar application, salicylic acid, and we're going to continue in that line, do more study in the communication, soil science, and plant analysis. And then we had paper in the sustainability also, and in the journal Sustainability. And before that, we published in 2017 a paper in the journal Chemiosphere. And I think I am a bit worried about the time. Spent about just about 40 minutes. But if you're interested in contacting me, then please do so. My email address is sgreips@kennesaw.edu. So thank you very much for attending my lecture. Thank you again.